Section 7.12, Formation Constants. A formation constant expresses the interaction strength of a ligand relative to the solvent molecules. The solvent is almost always water, unless specified otherwise. So now let's look at one example here. This is hexa-aqua iron 3 reacting with this ligand, thiocyanidal, and then form this transition metal complex. Now you have only 5 water ligands and this new ligand SCN. The name of this is penta-aqua thiocyanidal iron 3. Well, you see there are 2 plus charges here, but this SCN has a -1 charge. Therefore, this iron still has a 3 plus charge. Plus 3 minus 1 is equal to plus 2. And all these 3 species are in the aqueous solution. For water, this is a solvent, so we'll just specify this is liquid water. We'll assume the concentration of pure water is 1. And then now look at this formation constant. We put the products on top, reactants on the bottom, and over here water is the solvent. So we would say the concentration of this water solvent is very close to that of pure water. So it's just 1 here. The brackets in this equation denote the concentration now in molar or mole per liter solution. There can be multiple steps in this reaction. So over here, this M is bonded to N solvent ligands. It may react with N new ligands to form Ml sub N. So this is a new transition metal complex with N new L ligands bonded to M. And then this are N solvent molecules. So again, in this case, M, S, L are metal, solvent, and ligand. It can be simplified to this if we neglect the formulas or notations for the solvent. But you always need to keep this in mind when you see this kind of reaction. This M is bonded to the solvent molecules. And by forming new bonds with the new ligands, small solvent molecules are released. So now let's look at the multiple steps involved in this reaction. So first, over here, 1 water can be replaced by this ligand. Now the second water is replaced by the ligand. And over here, okay, in this situation, there's only 1 aqua ligand bonded to M on the left-hand side. The last water ligand is replaced by this L to form this final product, Ml sub N. Now this transition metal is no longer bonded to any solvent ligand. It's bonded to just N such L ligands. And then we can write out the formation constant for each of these N steps, Kf1, Kf2, all the way to Kfn. Over here, we are replacing the first water, the second water, and then this is to replace the last water ligand or aqua ligand with L. And then we can write out the equations for this N formation constants. Overall, there's a formation constant, beta sub N. Beta sub N is written in this form. So this is the final product. Over here, this M is bonded to N aqua ligands. And then beta sub N is equal to the product of Kf1, Kf2, all the way to Kfn. We can prove this. We can look at the product of all this N formation constants. We can write out their expressions, and you will see this M sub L and this M sub L cancel. And then this this ML and this ML cancel. ML sub 2, and over here that's going to be ml sub 3 over ml sub 2 times L. So this ml sub 2 cancels this ml sub 2 here. Okay? And then eventually there's going to be just ml sub n on top. On the bottom, it's just this metal. Well, this is really a metal bonded to the solvent molecules times L to the power of n, because you have L here, L here. In each of these n expressions, there is one L on the bottom. So overall, it's L to the power of n. And this is the so-called overall formation constant. The shorthand notation is beta sub n. Those are formation constants for this reaction for different metals and different ligands. Again, we're assuming the solvent is water. So really, we are replacing one water with the new ligand. So over here for magnesium 2+, we're using ammonia to replace one water. We're replacing one water with new ammonia. And this formation constant is less than 1. That means calcium 2+ prefers to be bonded to water than to be bonded to ammonia. And then you have nickel, in this case, 525. That means, well, nickel 2+ prefers to be bonded to ammonia than to water by a factor of roughly 500. And then you can see different metals reacting with the same ligand. This is ammonia or amine ligand. And then different metals reacting with chlorido ligand. You have different constants here. And then different metals interacting with this thiocyanidal ligand. Different constants here. And then finally, the ligand is pyridine. The transition metal can be iron, zinc, copper, and silver. And you get different formation constant here. In this column, and this column, they are the logarithm of the formation constant with a base of 10. There's also a dissociation constant, case of D. The dissociation constant is simply the reciprocal of the formation constant. The equation is like this. We are replacing this ligand L with one solvent molecule. So really over here, this M is now bonded to a solvent molecule. And then we can see this Kd sub 1 is this, M times L over M sub L. Kd2 is this. Now you have ML2 on the bottom, and the Kd2 is the reciprocal of Kf2. Again, the dissociation constant is the corresponding reciprocal of the corresponding formation constant. And then finally, you have Kd sub n. It's the reciprocal of Kf sub n. Over here, again, we are not specifying the number of solvent molecules bonded to M right here. So there can be 0, 1, 2, 3, 4, 5 water molecules bonded to M here. And then on the right-hand side, there is just one more solvent molecule being bonded to the metal.